Okay, we are going to start chapter number 4, network layer, the control plane. Okay, so we would like to discuss that the goal of this chapter is that we would like to understand principles behind network control plane, and more specifically we will discuss traditional routing algorithms, HDN control plane, and an error reporting protocol which is called internet control messaging protocol, and then we will discuss network management. Okay, so let's start. As we have discussed that there are two functions of network layer. uh, First is that routing. Routing means when a source want to send a message or packet to destination, so the first thing that the source has to do or the network layer has to do uh, to find a best route. This is called routing. That is, the network layer at the source node has to determine route taken by packets from source to destination. And computing, because we know that there in a network we may have more than one paths, so we have to compute the best path. This is called a routing algorithm, and this is the functionality. This is called control plane. So actually control plane is controlling the movement of data packets. Okay, and once the route is computed, then the packet is forwarded. That is, the packet is moved from source node to the first router, from the first router to the second router, till it reaches to the destination host. So forwarding means move the packet from router's input port to appropriate router output port. Okay, so we have two functionality. One is the control plane, that is computing the route from source to destination, and another is the data plane, that once the route is computed and the packet is moved on, the packet is forwarded along that path. So we have in chapter number 4 we have discussed data plane, and now we are going to discuss the control plane in detail. So we also know that for the network layer we have actually discussed that uh, we have two types of approaches for the network control plane. The one is called power router control plane. This is called traditional network, that is currently used in practice. Nowadays we are using the traditional network. So in this traditional network, each router has control plane. Each router has control plane, and that is the control plane of each router. It communicates with the rest of the control plane with the rest of the routers, and compute the best path. This is called traditional networking, or this is called per router control plane. And another is called SDN, software defined networking, in which the control plane is for all the routers is implemented on a centralized server, on centralized entity, that is called centralized controller. It is called controller. Okay, so as we know that in per router control plane, each router each router has control plane. Each router has a control plane, and this control plane, it communicates with the control plane with the routing algorithm of the other routers, and based on their communication with the rest of the routers, then this routing algorithm, it computes the forwarding table. Okay, so individual routing algorithm components in each and every router interacts with each other in control plane to compute forwarding table. Okay, so this is called per router control plane, or this is called the traditional networking. That is, the control plane is present in each and every router. This is called per router control plane. Okay, So it means that each router, it has a control plane, it has a routing algorithm, so it computes the best path for that router. Okay, this routing algorithm, it computes the best path at this router. But when it is computed, then it interacts with the rest of the with the rest of the switches. So this routing algorithm, it compute this path with the consultation of the routing algorithm at different stored at different switches, and this uh, routing algorithm at this switch, it will compute the forwarding table for this switch. Okay, so we have already discussed it. Second is called logically centralized control plane. As we have discussed that the control plane is separated from each router. Okay, the control plane is separated from each router, and the control plane is implemented on a server. Okay, this server is called remote controller. This is called remote controller. Okay, so you can see that the in the SDN or in the logically centralized control plane, the control plane from each router, it is taken to a remote controller, and this controller communicates, or this controller compute the routing path for each router. Okay, so there is a centralized control plane that computes the path for each router. Okay, so a typically remote controller interacts with the local agents, with the local switches and routers to compute the forwarding table. Okay, so we have already discussed this, that the control plane in the HDN, it is separated from the switches. The control plane is separated from the switches. It is implemented remotely at a server or more than one server. Okay, but you can see that in the per router control plane, the control plane is present in each and every router. Control plane is present in each and every router. But in SDN, the control plane, it is separated from each router. The control plane is separated from each router, and it is implemented on a remote entity, a remote server. Okay, now we are going to discuss the routing protocol for per router uh, per router control plane, that is for traditional networking. So we are going to discuss the routing protocol that are used at the control plane for the traditional networking, that is per router control plane. So we have uh, two types of routing protocol. One is called link state routing protocol, and one is called distance vector routing protocol. Okay, so what is a routing protocol? We know that the routing protocol, it basically determine, or it basically compute the good path or best paths are equivalently routes from sending host, from source to destination machine through the network of routers. Okay, so the path, it is basically sequence of router that routers packets will traverse in going from given initial source host to given final destination host. So basically routing path, it is consists of the that when the source send to a message to destination, then the packet should be forwarded through which routers, okay, in which sequence. And the path, it can be good, it can be called good path. That path is good which has the least cost. Okay, or that path is good which is fastest, which has higher bandwidth. Or that path which has less congested, that is which has low traffic. So if we had it low traffic, then we can then the data can be moved fastly. And this routing, it is also one of the top 10 problem in the networking, in the computer networking. Okay, so I would like to emphasize that whatever is the whenever we want to solve any problem, so the problem can be solved efficiently if it is put in some model. Okay, so we would like that the routing protocol, the network, it can be represented in the form of graph. Okay, suppose this this is a graph. Okay, in a graph we have two things: nodes and edges. You can, in this graph we have nodes u, v, w, x, y, z. These nodes, they represents the routers u, v, w, x, y, z. Okay, and the edges, when this router is connected with this u router is connected with the v router, so it's called this is the edge. U router is connected with v, so it will have an edge, a link, an edge, and each link will have its cost. For example, u and v, they are connected through a link that is 2 meter wide, so its distance is 2, and u and w, they are connected through a link which is 5 meter, for example, long, so its cost is 5. So the cost, it can represent the distance of the link. It can also represent the bandwidth. For example, this is the link which has 2 MB bandwidth. This is the link which have 5 MB. This is the link which is 3 MB. Okay. So in the graph we have two things. First is nodes. Nodes can represent the routers. The links that it are the edges. E is called edges. Edge represents the link. When the two routers, they are connected directly, then there is a edge present. So edge is also called set of links. So link is what? For example, uv, this is a link, and ux, this is a link, vw, this is a link. Okay, similarly xw, this is a link, xw or wx. Okay, and each link has a cost. For example, 2, 2, 3, 5. And what a cost represents? The cost can represents the bandwidth. Okay, so if this cost is representing the bandwidth, then we should forward the data from u to z, for example, from u to z. So the path should be that one which has higher bandwidth. Okay, okay, so that path will be best one which has the higher bandwidth. But if this cost is representing the distance, for example, this is 2 meter distance from u to v, from v to w it is 3 meter, then we should select a path from u to z such that which has the least cost. Then the least cost path, the least length path, it will be the best path. Okay, so anyway, so when the whole computer network it is represented in the form of graph, then it is easy to find the path from one router to another routers. So it analogy can be that, for example, if these nodes, they are representing the cities, for example, U, Peshawar, Islamabad, Karachi, Lahore, etc., and the links, they represents the roads between two cities. For example, for U, we have a road, V, from V to W we have a road, and from U to W there is also a direct route, a direct road. So you can see that which one is best one, then you can decide it easily. Okay, so once the computer network it is represented in the form of graph, then then it is much easier to compute the best path from one router to another router. Okay, so this is important. Okay, we will discuss it later on. Okay, now each link has a cost that we already discussed. The cost is represented by c. C means cost, x dash, from node x to x dash. So this is the cost of link x dash. For example, the cost from w to z, this link, this its cost is 5. Z to y, its cost is 2. Okay, so when we decide, when we have this graph and their links and the cost of each links, then we can easily compute that from, if we want to move from u to y, then which path has a minimum, which path is best one. That path will be best one depending upon the cost. For example, if the cost is representing the bandwidth, then we should take that path which has the higher bandwidth. Okay, for example, this path is higher bandwidth, and we should, if this cost is representing the distance, then we should take that path which is the which has the least distance. Okay, so before coming to this slide, that the routing algorithm, they can be classified into different categories, so I would like to explain uh, first the link state routing protocol, and then we will come to know that what does this mean. Okay, so a link state routing protocol or a link state routing algorithm, how it works. Okay, first we would like to understand it. In a link state routing algorithm, we have some steps. Okay, for example, in step 1, each node computes its link state information. So first is, what is link state information? Link state information means that if, for example, I am considering node u, so what are its links? So its links are ux, uw, uz. It's, that is the link, it's directly connected nodes, it's directly connected nodes, or it's directly connected links, they are called link state information. So the link state information, it represents the links are the direct neighbors of a node. So you can see for u, the link state information is ux, uw, and uv. And what is the cost of each link? For ux, its cost is 5. uw, its cost is 3. uv, its cost is 7. Suppose this cost, it represents the distance. For example, ux, it is at the 5 meter, uw, it is at 3 meter, and uv, it is of 7 meter. Okay, similarly, what should be the link state information for node z? So node z, it has two neighbors, y and x, direct neighbors. So zx, its cost is 9, zy, its cost is 2. So this is the link state information. So each node first has to compute its link state information. In a link state, the first step is that each node computes its link state information. So for example, u, z, similarly y will compute its link state information. So it will be contain yv cost 4, yw cost 8, yx cost 7, yz cost 2, and similarly. Okay, so each node has to compute its link state information. This is the first step. Okay, now the second step is that each node broadcasts or floods its link state information to all the nodes in the network. When each node computes its link state information, for example node u, it computes its link state information, so it should be, then node u will broadcast to all the nodes about its link state information. Okay, that is what. Now how broadcasting is performed. Suppose u node wants to broadcast, suppose node u, it wants to broadcast its link state information. So what is its link state information? The link state information of u is ux equal to 5, uw equal to 3, and uv equal to 7. So how it will broadcast? So it will generate a message, and that message it will send to its neighbors. Okay, so what will be the destination address of this message? So the destination address, it should be broadcast 255.255.255. This will be the destination IP address, that this packet is for all the nodes. Okay, so when this, what does it mean? When the x node receives the message, okay, so it contains 255. So 255 means that it is for every nodes. So it is also for the x. So x will extract this information. It will store this link state information that is stored in the message. Except it means that this information, that is the link state information that is stored in this packet, it will store with itself. And also it will, and when a packet has a destination address 255, what does it mean? It has two meaning. First, accept it. Every node will accept it. For example, x receives, so it will accept it. Accept it means that it will store this information with itself. W, it will store this information with itself. V, it will store this information with itself. Okay, and forward further, when the packet is received with the destination 255 by any router, so it accept the message and it forward further this message to all, because this message for all the people, so all people means that it should be forwarded to Z, because it is not reach when you send it, so you will directly send to X, W, V, they are connected, so you cannot directly send to Z. So the X will forward it, X will forward it further to its neighbors. Okay, so this is the information. But you can know that, for example, so you can see that when this X forward this message further, for example, X received the message, X, it accepted this information and stored it with itself. Now because the address is 255, so it accepted, and now it has to forward further, so it will forward to its neighbor. Its neighbor is Z, Y, and W, and U as well. It will not forward to U. Why? Because this message has arrived from you, so it is arrived from you, so it will not forward to that again, because this information is already with you. Okay, now one important thing that you can note, that W, it receives this same information from U and from X. Okay, so the same message is received by W two times, one from U and one from X. Okay, so if and this message which is received from here and from here, it will have the same link state information, it will have the same destination, it is 255, so it will accept it and forward further. So if it forward further, then it will retransmit to U, V, and this, so it will create redundant messages, it will create redundant messages. To avoid these redundant messages or duplicate packet transmission, duplicate packet forwarding, we have this mechanism, because this message also have the source IP address. What is the source IP address? The source IP address is U, IP of U. And whenever the message is generated, there is an identifier. There is an identifier. Okay, we have discussed it in the IP protocol. Okay, there is an identifier 9. Okay, so suppose this identifier is 9. So by using this IP and 9, when this message is sent, it has the IP source IPU and identifier 9. When X forwarded further, it also has the source address IPU and identifier 9. That this message is generated by IPU and its identifier is 9. So through source IP address and through identifier, this W can understand that this message that is received from X, it is duplicate. Why? Because it is already received from U. It is already received from U. So when the duplicate message is received, the duplicate message is identified from IPU and identifier. Okay, so these two values, they are unique identifying that whether this message is duplicate or not. If a node receives two messages with the same source IP address with the same identifier, then this is the duplicate message. The duplicate message, they are not accepted nor forwarded. The duplicate message are not accepted. So in this case, when you receive the this message from when W receive the message from you, so this is for the first time, so it will be accepted and it will forward it. But when it is received from X, so this message, it will have IPU and identifier 9. So from source IP address and from identifier, the W can identify that this message is duplicate. Okay, it is duplicate. Why? Because it is already received from you. So if it is duplicate, then it will not be accepted. Accepted means that it will not process it. It will discard it directly. It will discard it direct. So this message, it will be discarded. It will not be accepted and not it will be forwarded. Okay, so in this way it controls the flooding. Okay, but X will forward it to W, Y, and Z, and you can see that W have received it duplicate message, but the duplicate message is identified. Why? The duplicate message is identified by using the source IP address and identifier. If the two messages they are received, they have the same source IP address and same identifier, it means that they are duplicate. If they are duplicate, then they should be discarded. Okay, so similarly X will forward it. So now you can see that the message that is forwarded by you, okay, it is sent by you, it has the link state information of you, it is received by X, W V, it is also received by Y and Z. Okay. Now similarly the node V, it will also forward it further. V node will also forward it. So you can see that V node forward to W. So this is the sniper. It will not forward to V, will not forward to U. Why? Because we have received from U, so it will not forward to U, but with the rest of it will forward, we will forward it to rest of the neighbors, so it will be forwarded to W. When it is forwarded to W, so it will have the same source IP address, IPU and identifier 9. So from source IP address and from identifier, the W can identify that this message is duplicate. If it is duplicate, it will not accept it, it will not forward it, it will discard it directly, it will be discarded. Why? Because it is already received from you, it is already received from you. Okay. When it similarly, when the V is forward the message to Y, so Y have already received message from X. So by using the IP source IP address and identifier, this Y can identify that this message that is forwarded from V, it is the duplicate, so it will be discarded. Okay. Similarly, now you can see that the similarly the node W will forward it to its neighbors. So you can see that the link state information of U, it has reached to X, W, V, Y and Z, to all the nodes in the network. So there are two steps. The first step is that each node computes its link state information, and then each node broadcasts its link state information to all the nodes. So we have just shown that how the link state information is broadcast by U to all the nodes. Similarly, we will forward its own link state information to all the nodes. W will forward its own link state information to all the nodes. So if Z node, it receives the link state information of U, X, W, V, Y, and it has its own links information. So from these link state information, it does node Z, it can compute this graph. It can compute this graph. So the third step is that each node construct the graph from the link state information of all the nodes. Similarly, node U, it will construct the graph W, V, Y, because each node have the link state information of all the nodes, and each node also have its own link state information. Okay, so it will construct this graph. Okay, so I think it is easy. Once this graph is constructed, then we have to compute. Now once this graph is constructed, each node has this complete graph. Now for example, a node U, it wants to compute the best path, then it can compute on this graph, because it is easy to understand. Okay, so you can see that there are, if you want to compute the shortest path from node U to Z, from node U to Z, so what is the shortest path? Obviously a simple approach is that you will compute the all possible paths from U to Z. For example, this is the one path, its cost is UV7 411 into 13. So this is one path, its cost is 13. This is another path, its cost is 3 plus 8 11 12 13. This is another path from here to here to here, so its cost is 3 3 6 4 10 and 2 12. Okay, so this approach is not good. Why? For this, why? Because we may skip some path. Okay, so for this purpose we have some algorithms. So one of the algorithm is called Dijkstra algorithm. It is a systematic approach. It will compute the path from U to Z, not only from U to Z, but it will compute shortest path from U to X, W, V, Y and Z in 6 steps or 5 steps. So, and it will not skip any path, any link. And so now we are going to discuss the Dijkstra algorithm. So there are the link state routing algorithm. It has how many steps? First step that each node computes its link state information. Second step, that each node broadcasts its link state information to all the nodes. Once a node has the links to information of all the nodes, then in the step 3, each node construct the graph. Once the graph is constructed, then each node compute the shortest path by using the Dijkstra algorithm. So now we are going to discuss the working of Dijkstra algorithm. Okay. Suppose we want to compute the shortest path from U to all the nodes. Okay. So this is the n dash. N dash means the visited nodes. So at the first time we are starting from U, so U will be the visited. U will be the visited. Now we want to compute the distance. Distance V means the distance from U to V. The distance from U to V. Okay. And PV means the predecessor. That if we want to move from U to V, then which is the next node? Which one is the previous node? Okay, so we will discuss it. Now suppose if I'm present at the node U, so a node U is in the visiting list. Okay, so from U I can only access X, W and V directly. So these are directed path. So the cost from U to X, it will be 5. From U to W it will be 3. From U to V it will be 7. And from U to Y it is infinite, because from U I cannot access directly Y. So if I cannot access directly, then it means that it is infinite. So similarly from the cost from U to Z it will be infinite, because when I'm standing at U, so at this moment I only know about U, because U in the list. So I only know about U. Okay, so if I am standing here, so I can only access this link and this link directly. Okay, so you can see that this is the path. Now these are the links that are explored and these are its cost. Okay, now when this is computed, okay, so which one is the lowest one? This is the cost 7, this is 3, this is 5, and the previous node is U, because if you want to reach from U to X, its cost is 5, and the previous node is U. Okay, so you have reached to X from U directly. Similarly, you have reached to W from U directly. Okay, so this represents the previous node and this represents the distance. So at the moment, if we are standing at U, so from U we can reach to X, W and V. From UX the cost is 5 and the previous node is U. The previous of X is U. Similarly, from U to W its cost is 3 and the previous node of W is U on this link. Okay, similarly the distance from U to V, it is 7, and the previous node on this link, on this path is the previous node of V is U. Okay, and the cost from U to Y is infinite. Why? Because if I'm standing here, so I can only go through these links. I don't know about the other links. So these costs are infinite. Okay. Now after computing the cost at each step, this is the first step. Okay. After computing the path at each step, now we have to select the least one. Suppose we have decided, as we have assumed, that this link cost or the edge cost, it represents the distance. So we should take that best path which is the least distance. So we have to select the least one. So least one is 3. So this is the shortest path. Okay. So this will be selected. This selection, what does it mean? That this is the distance of W. So this W will be added to the visited. Okay, and this path is the shortest path from U to W. Okay, so you can see that this is selected. So this is, now we have, in the first step we have computed the best path from u to w, and this path length is 3. Okay, and now this, when the shortest path is computed, then this node will be added to the w, to the n dash. This is the visited list. This will be added, the w will be added to the n dash. Why? Because we have found the shortest path from u to w. In the first step u is added, because if we are starting from we are starting from u, so the shortest path from u to u is 0, so it is already known. And the next step we have found the w, so we have found the shortest distance from u to w. So u to w, the length is 3, and the previous node is u. So this path is added, this one. Okay, now we have reached to w. Okay, now when we reach to w, so now we are going to explore the neighbors of the newly visited node. This node is now visited. Okay, so this node is in visiting list, so we are going to explore its neighbors. So its neighbor are which one? Okay, so we are exploring. The first neighbor of w is x. You can see that if we consider this link, then the distance from u to x, so from u to w it is 3, shortest path. From w to x it is 4, so 3 plus 4 it is 7. 3 plus 4 is 7 if you take this path. This is the first neighbor that is explored. And the already cast from u to x, is 5. So already cast is minimum, is lower than this new one. This is the new one link that is explored, and this new link, when it is explored, so it has the distance from u to x, so its cost is 3 plus 4 7, and the already cost is 5. So we will maintain the lowest cost, so this cost will not be changed. It means that this link is not on the shortest path, so we will bring it down as previous one, that this link is already shortest, the present value is already shortest. Okay, this is really protect. Now we are going to explore the another neighbor of w. Who is the next neighbor of the w? You can see that y. This is another neighbor. Okay, now we want to get to the distance. If we take this neighbor, this link, so the cost from u to w is 3, and w to y is 8. So if you want to reach from u to w and w to y, so the total distance will be 3 plus 8. It is equal to 11. It is equal to 11. And the already cost from u to y, it is infinite. So it means that the present value is higher, and the new value that is explored, this new value that is explored, it is minimum. It is 11. So 11 is less than infinity. So we will consider this lowest one. In the previous one, the 3 plus 4, it was 7, and the present value was 5. So we would like to maintain the lowest one, so the present value is kept unchanged. Okay, and now in this case, from w to y, the cost from u to y, its distance is 11. 3 from u to w 3, and from w to y 8. So it 11, and the present value from u to y, it is infinite. So the new explored value, it is less as compared to the present value. So this value will be replaced. It will be replaced by 11. It will be replaced 11. And which one is the previous node? The previous node is w. The previous node is w. Okay, so we can see that this value will be replaced by 11. Okay, so when it is explored, the new neighbor, this one is explored, so if we find a new lower cost path to y, we found a lower cost path to y. Okay, and what is the previous node of y? In this case, it is w. Okay, now we are going to explore another neighbor of W. Okay, this is the another neighbor. You can see V. This is the another neighbor. If it is explored, then the cost from U to W is 3 and W to V is 3. So the cost from U to V through W, it is 3 plus 3, 6. 3 plus 3, 6. And the already cost present from U to V, the already cost is 7. So the new explored one is less than the present value. The present value is 7 and the new explored one is the 6. It is lower. So we will replace this present one value with the new one. So it will be also replaced. Okay, it will become 6 because this is the new explored value is minimum. So the new explored value will be placed if it is less than the present value. If the present value is less than the new explored value, then the present value will be maintained. Okay, so we always maintain the minimum value. Okay, and in this case the previous node of V is W. Okay, now we are going to explore the next neighbor. The next neighbor that is of W is this one, U, and this U is already in the visited list. What does it mean? That for U we have already the shortest path. Okay, the node are added in the dash in the visited list once their shortest path is found. So if their shortest path is already found, then we don't need to recheck to recompute the another path. Okay, so its shortest path is already found, so we will not consider this one. Okay, so now we have explored all the neighbors of W, X, Y, V and U. So there is no other neighbor of W. So all the are explored. Okay, so these values are updated. Now this value is not updated, so it will be kept. It will be as the present value. Okay, so it will be present. And this value, the 3 view, it is not kept. Why? Because the shortest path is computed already. So its shortest path is computed, then it is finished. Its work is finished. Okay, so it will not be carry on in the next steps. Okay, now this second step has been computed successfully. Okay, now which one is the minimum value? Which one has the minimum distance? So you obviously this is the minimum distance, 5. This is 6, this is 5, this is 11, this is infinite. So which one is the lowest? 5 is the lowest. So it means that this will be added into visited list. You can see that 5 will be the dx will be added to the visited list. Okay, 5. And now which one is the previous node? In this case the previous node is U. So this link is added. Okay, you can see that this link is added. Okay, now we are going to explore the neighbors of X. So we have reached to X. So we have found the shortest path from U to W and from U to X. Okay, so U, W, X, they are added in the visited list. Their shortest path is found. So now we have reached to X. So now we are going to explore the neighbor of X. Now we are going to explore the neighbors of X. So what are the neighbors? The first neighbor is W. W is already in the visited. What does it mean? That for W we have already shortest path. Its shortest path is already computed. So if it is computed, then we don't need to explore it. Okay, so we will not consider it. Now we are going to explore the next neighbor of X. The next neighbor of X is Y. This is the neighbor. So this link is explored. Now this link we would like to check it. Now the distance from U to X, the shortest distance is 5. It is 5. And from if we consider this path, that is, if you consider U to X, it is shortest path, it is 5, and from X to Y it is 7. So if you consider U to X and X to Y, so it will becomes 12. And the already path from u to y, it is 11. The present value is 11. So the present value is minimum, is lower than the explored one, so we will maintain the present value. Okay, the minimum value, this will be maintained. Now we are going to explore the next neighbor of x. So we have explored the neighbor of x, w and y, they are explored. Now we are going to explore the next neighbor. So which one is the next neighbor? This is the z, this link. Now if you consider this link, so the shortest path from u to x is already computed, is 5, and from x to z, if you consider this new explored link, then it's 9. 5 plus 9, 14. So the distance from u to z, yx, it is 14, and already distance from u to z, is infinite. So the new explored one, its value is less, it is lower. So we will maintain the minimum value, the new explored one. Okay, so it will be maintained, 14 and x. 14 is the distance from u to z, if you consider this link. Okay, and the previous node on this path is for u is for z, it is x. So the previous node is x. The previous value of z in the previous node of z is x. The previous value of z is x on this path. Okay, so we have explored this neighbor of x, this neighbor and this neighbor. Okay, so we have explored all the neighbors. Okay, we have explored all the neighbors. So all the neighbors are explored. Now we will, these two values, they are for this shortest path is already computed, so they will be not maintained, they will be not carried on in the next steps, and this will be carried on because it is not okay, it will be carried on. Okay, now the third step, it is also computed successfully, and now which one is the minimum one in this step? In this step, which one is the minimum distance? So the minimum distance is this one, 6. 6 is the minimum distance, and this is the distance of u, to v. This is the distance of v, and its previous value is w, that is, this is the path from u to w and w to v. This is this is stored already, 6w. Okay, so we will include this link. Okay, so we will select this as the shortest path. So the shortest path toward v is computed, and it is how much? It is 6. So we will be able to visit it. And which path is the minimum? 6w, means that this path, the path from u which has the previous one w, not the previous one which has the u. Okay, so this is the path that has the previous value w, so it is the path from u to w and w to v. Okay, so w to v, this is the shortest path. Okay, so now we have computed the shortest path from u to w, u to x and u to v. Okay, so now we have reached to node v. So now we are going to explore the neighbors of v. So who are the neighbors of v? The first neighbor of v is u, and you know that u is already visited. The path for u is already computed, so we will not explore it. Okay, we will not consider it. Now we are going to consider the next neighbor of v. So the next neighbor of v is y. Okay, so we can see that y is not in visited list, that is, for y shortest path is not computed yet. So if we consider this link, so the shortest distance up to v, it is 6. 3 plus 3, 6. 6 plus 4, 10. 6 plus 4, 10. So if you consider this new explored ring, then we can have the shortest path from u to w, w to v, v to y. So its path will be 3 plus 3, 6. 6 plus 4, 10. Okay, and the already shortest path is 11 to y. Already shortest path to y is 11. It is 11. So then this new explored link, it gives us the shorter path. So we will consider the the shorter one, the new explored one. So it will be replaced. It will be replaced one 10v. Why? The 10 is the distance, and which path? Because y have the path from x w, but pv, the previous one value is v. It means that this one path, not this one and this one. Okay, so this path is the shorter one and the distance is 10. Similarly, for so now we have explored all the neighbors of v, because we have reached from a to v from w, so this link will not be explored. Okay, so this link and this link is explored. Okay, now the remaining now we know that its shortest path is computed, so it will not be carried on in the next step. Okay, and now this 14x it will be carried out. Okay, because its shortest path is not computed. Now in the fourth step we have the values 10 and 14. So which one is the minimum? This one is the minimum. Okay, so this one will be added into visited list. That is the shortest path for y, it is minimum, so y is added into visited list. That is the y shortest path is computed. And which one is the shortest path? It y, which is the previous value v. So the y, it has shortest path. And which one is the shortest path? This one or this one? So we consider that the previous one value is previous value of y v. So that path which has the previous one value v. So this is the previous one v. So this link is explored. Okay. So now we have computed the shortest path from u to w 3, from u to x 5, from u to v 6, and from u to y 10. Okay. Now we have reached to y. Now we are going to explore the neighbors of y. So who are the neighbors of y? The first neighbor of y is w, this one. This w is already in visited list. That is, for w we have already computed the shortest path. So it will not be considered. It will not be considered. Now the next neighbor of y is x, and the shortest path for x is already computed, so it will not be considered. So the next neighbor is z. This is the next neighbor of z. Okay, so if this new explored link is considered, then the shortest path up to y is 10. It is 10. So if we consider this link, then from u to w, w to v, v to y, it is 4. It is 10. 10 plus 2, 12. So if we consider this path, then it will be considered to 12, and the already path to z is 14. So this new explored path, it gives us shorter path. So we will keep the shorter path. So this we will consider this new explored links. Okay, so it will be replaced by 12, because this explored link it gives a shorter path than already present. Already present is 14, and the new explored link it gives us 12. Why? Because up to y the shortest path is 10. 10 plus 2, 12. So we can reach from u to z, from u to w, w to v, v to y, y to z. So its cost is 12. Okay, and already present cost is 14. So you can see that at z which path is 12. So we can differentiate it by using y. Y the previous value of, and this path is y, and this path the previous value is x. So we will consider this path. Okay. Now all the neighbors of y are explored, and now there is only, so this step is completed. This is already computed. So there is no other values to be carry on. Okay, so it means that this value is shortest one, because this is the only value, so it will be added. Okay, now the shortest path from y to z is also explored. So now we have computed the shortest path from u to all nodes. From u to w is 3, from u to x is 5, from u to v is this one, from u to y is this one, and from u to z is this one. Okay, so this is the shortest path from u to all the nodes. So this is how the Dijkstra algorithm works. Okay. Now after computing, now the fifth step. What is the fifth step? The fifth step and the last step of the link state routing protocol is that it computes this forwarding table. This forwarding table from this graph, this shortest graph, the red one. Okay. The destination W, its distance is how much? 3. Its distance is 3. And if you want to move from U to W, the distance is 3. And if you want to move from U to W, so which one is the next hop? So the next hop is W itself. W itself. From U to X, its cost is 5. Its distance is 5. And if you want to move from U to X, so which one is the next hop? So the next hop X is itself. If you want to move from U to V, so if you want to move from U to V, so this is the shortest path. So its distance is how much? 6. And if you want to move from U to V, the next hop is W. So we have to move through W. So the U have to forward it to W. Then from W it can reach to V. Okay. So the next hop is this case in W. So the shortest path from U to Y, it is how much? It is the 10. And if you want to move from U to Y, then the next hop is W. Next hop is W. Similarly from U to Z, its cost is 12. And if you want to move from U to Z, the next hop is 12. That you have to move through 12. You have to move through W. Okay. So the next hop from U to Z on the path is W. Okay. So this forwarding table is constructed. Okay. So we have so these are the steps involved in the link state routing protocol. Okay. So we have discussed the link state routing protocol and its working. So the first step is that each node computes its link state information. Each node flood its link state information to all the nodes, and each node construct the graph. And after constructing the graph, then each node has to compute the shortest path by using the Dijkstra algorithm. And once the shortest path is computed, then the final step and the fifth step is that of to compute the this forwarding table. Okay. This forwarding table. Okay. So we have discussed the Dijkstra algorithm. Okay. So we have discussed the Dijkstra algorithm, that the network topology are linked cost, they are known to all nodes. Okay. So how the nodes come to know that all the nodes, they have the linked cost of all the nodes. So this is accomplished by link state broadcast, that each node broadcasts its link state information to all the nodes. So it means that all the nodes, they have the whole link state information of each and every nodes. So each node have the same information. So each node have the topology and the link cost of all the nodes. Okay. Then each node computes the least cost path from one node to another by using the Dijkstra algorithm. Okay. So when the path is computed, then the forwarding table is built up. Okay. So this is actually iterative approach. It is iterative approach. Okay. So it means that if for example, if we have here, for example, in this here, if you want to you is going to find the path to X, W, V, Y, Z, to 5 nodes. To how many nodes? 5. So if a node want to find the path to 5 nodes, so in each step, in each iteration, the node is computing the shortest path to each node. For example, in the first step, the node U has computed the shortest path to W. And the next step, the U has computed the shortest path to X. And the third step, the U has computed the shortest path to V. And in the fourth step, the U has computed the shortest path to up to Y. And in the next step, the U has computed the shortest path for node Z. Okay. So in each iteration, the node computes the shortest path to a destination, to one destination Okay, so these notation are used. Cx means the cost, general cost. For example, the link cost. For example, here the link cost is 5. Here the link cost from x to y is 7. Y to w is 8. Okay. In dv's, it is the current value of shortest distance from u to v. From u to v. Okay, and this is the predecessor, the previous node along the path. Okay, and in dash it is the set of nodes whose least cost or is path is definitely known, that it is already computed, who for whose shortest path is computed. So this is the list or the set of the nodes for whose shortest path is computed. Okay, this is actually the pseudo code of Dijkstra algorithm. This is actually the pseudo code of Dijkstra algorithm. Okay, and this is another graph. So you can compute the shortest path from u to z by yourself. Okay, so I think it is much easy. Okay, so we have discussed it. Okay, so we have discussed the Dijkstra algorithm.